All right, so we've talked about and looked at qualitative aspects of Le Chatelier's principle. Um, we talk about, okay, what's going to happen to the amounts of each of the substances once equilibrium is reestablished? Well, this is going to go up, and this is going to go down, and this is going to go up. Well, now let's quantify this. So you do something to disturb a system at equilibrium shifts a particular direction, and the amounts of each of the substances change. Well, what do they change to? That's what we're going to do here. So let's take a look at example 17.1, the top of page 681. Read along, please. So some hydrogen and iodine are mixed at 229 degrees Celsius, doesn't matter the temperature really, in a 1 liter container. When equilibrium is established, the following concentrations are present. If an additional 0.300 moles, notice that we're given concentrations, and then we're given an additional amount in moles, 0.300 moles of HI is then added. What concentration will be present when the new equilibrium is established? All right, so here's what we want to do. First thing is take our equilibrium concentrations and calculate the value of K. So we get K is equal to 50. Hopefully you can see that there in the solution. And then what we're going to do is we're going to set up, this is not an ICE table. It's almost like a SCAR table. So you start off with your equilibrium concentrations, and those are kind of like the new initial concentrations, if you will. So in the book, it labels them equilibrium concentrations, so 0.08, 0.06, 0.490 for H2, I2, and HI respectively. And then I prefer to do things with moles because sometimes it gets a little tricky using molarities, but they're going to use molarities here. Um, Again, the moles and molarity are the same number since it's in a 1 liter container. But if it's not a 1 liter container, then we have to take that into consideration. So let's just look at what we have here. So you add 0.300 moles per liter of HI, and you don't add any more H2 and I2. And so now we have what the book calls new initial concentration. So right after the stress is applied, what are the concentrations of each of the substances before the equilibrium has a chance to shift? So 0.08, 0.06 for H2 and I2 respectively, and now we have a new initial concentration of HI, 0.790. Next, what we do is calculate Q. So take those concentrations, our new initial concentrations, and calculate Q. So we see Q is 130. Well, that means that Q is greater than K. So equilibrium exists only when Q is equal to K. So what has to happen to Q? Q needs to decrease. So what direction must the reaction proceed so that Q decreases and we reestablish equilibrium? Now this one's pretty easy because you're increasing the amounts of the product, so we know the equilibrium is going to shift to the left, but sometimes it's not too clear. So you want to confirm that direction of shift by comparing Q to K. Equilibrium needs to shift to the left. Here's the tricky part. Once we know that the equilibrium shifts to the left, we need to then set up another ICE table. So take a look there in the solution. We take our new initial concentrations, plug them in for I, and then look at the change. So because the reaction shifts to the left, the equilibrium shifts to the left, the amounts of H2 and I2 are going to increase. So they're given a plus X. And the amount of HI is going to decrease. So we do minus 2X. And so now we have our new equilibrium concentrations, 0.08 plus X for H2, 0.06 plus X for I2, and 0.790 minus 2X for HI. Next step, take those equilibrium concentrations, plug them into your equilibrium expression. Remember, we had previously calculated K as being equal to 50. And then we solve for X. Well, we have a quadratic equation, 46X squared plus 10.2X minus 0.38 equals 0. So how do we solve for x in a quadratic equation? We use, of course, the quadratic formula. So we plug our values into the quadratic formula. It says, read along please, solution by the quadratic formula gives x equal 0.032 and negative 0.25. So make sure you identify that extraneous roots, negative 0.25, that doesn't make sense, that's not going to work. And so x is 0.032. Plug that in and get your new equilibrium concentrations. So notice that H2's concentration increases. It was 0.08, now it's 0.112. I2's concentration increases. It went from 0.06 to 0.092. And notice HI, we talked about this. We said the equilibrium will shift in a way that partially counteracts the stress, partially counteracts. So you added an additional 0.30 molar, but what happens? What do you notice happens to the amounts of HI? Initially it was 0.490 molar, you add 0.300 molar, and our new equilibrium concentration is still higher than what we started with, even though the equilibrium shifts to the left. On the top of the next page, 682 just summarizes what we started off with, the stress that was applied, and our new equilibrium concentrations. So, calculate K, set up a kind of scar type table to find our new initial concentrations after you apply the stress. Calculate Q, compare Q to K to see which way the equilibrium shifts. If it shifts to the left, then the amounts of the reactants will increase, the amounts of the product will decrease. If it shifts to the right, the amounts of the reactants will decrease, the amounts of the products will increase. All right, try one. Number 63 on page 697. It's not quite that extensive, but we'll get there. Try that. Pause now, please. All right, so kind of part of what we did last time, or in the example problem. Plug in our concentrations, calculate Q is 0.375. The K, which was given to us in the problem, was 0.020. So we see that Q is greater than K. So in order for this system to reestablish or reach equilibrium, we need Q to go down. So we need the top to go down, we need the bottom to go up. Less products, more reactants. That means that the reverse reaction is favored, aka equilibrium will shift to the left. All right, next up, take a look at 1712, starting on 682. It says at 22 degrees Celsius, the equilibrium constant for the following reaction is 4.66 times 10 to the negative third. At 0.800 moles of N2O4 were injected into a closed 1 liter container at 22 degrees Celsius. How many moles of each gas will be present at equilibrium? That's part A. So set up our equilibrium expression. Concentration of NO2 squared over concentration of N2O4 is equal to our K, which is given to us. So we can set up an ice table. See that in the solution. N2O4 is going to decrease, NO2 is going to increase, and we solve for X. Again, we have a quadratic equation, so use a quadratic formula. And so X is equal to, where is it at? 3.00 times 10 to the negative second. So that's a concentration, mind you. The question asks for how many moles. So solve for X. So X is a concentration at equilibrium for the, plug that in into the ice table values there, and we get for NO2, the concentration equilibrium 6.00 times 10 to the negative second molar, and the equilibrium concentration of N2O4 is 0.770 molar. This reaction occurs in a 1 liter container, so take the concentration, multiply it by the volume, and you get moles. So 6.00 times 10 to the negative second moles of NO2, 0.770 moles of N2O4. Letter B. If the volume were then halved, How many moles of each gas will be present after new equilibrium has been established? So remember, when you change the volume of the container, that's going to cause the equilibrium to shift. So let's take a look at the solution for there. So we set up, again, kind of a SCAR table. So if the volume is halved, then the pressure is going to increase. So if the pressure increases, which way does equilibrium shift? It will shift to the side with less gas particles. So in this case, equilibrium is going to shift to the left. And so that means the amount of N2O4 is going to increase. So that's a plus X there. And the amount or concentration of NO2 is going to decrease. So that's a minus 2X there. So plug in those new equilibrium concentrations into our equilibrium expression and solve for X. So we get 0.086 molar for the NO2, 1.56 molar for the N2O4. So once again, though, we're asked to find moles once equilibrium is reestablished. Remember, the volume is now 0.5 liters, so take your moles and multiply it by 0.5 liters, and we get 0.043 moles for NO2 and 0.780 moles for N2O4. So notice that's the amounts of NO2 decrease and the amount of N2O4 increased as a result of that stress. Again, there's a summary there. First equilibrium amounts in moles, the stress, and then our new equilibrium amounts. All right, number 67, page 697. Give that a try. Pause the video. All right, so a little different setup. I didn't set up an ICE table here. So the values I got, though, you can think of getting those from an ICE table. First step is to write the equilibrium expression. So concentration of PCl3 times concentration of Cl2 over concentration of PCl5 is equal to the equilibrium constant, which we are given in the problem, 0.093. All right, if we set up an ICE table, what would be the initials? What would be the equilibrium concentrations? We know that's the equilibrium concentration for the PCl3, sorry, Cl2 is 0.17 molar. Well, remember that's because there's a 1-to-1 ratio, at equilibrium, you're going to have the same amount of Cl2 as PCl3. So if the concentration of Cl2 is 0.17 molar, so is the concentration of PCl3. So we know these equilibrium concentrations. We don't know this. So we'll plug in an X, which will give us our concentration of PCl5 at equilibrium. Be careful. That is not what we're trying to find. So if you have that much at equilibrium and you formed 0.17 molar of Cl2, again, thinking about the ICE table, that means the concentration of Cl2 and PCl3 went up by 0.17 molar. So that means the concentration of PCl5 went down 0.17 molar. So this is how much you have at equilibrium. This is how much the concentration changed by, but notice I'm going to add those because, of course, we have more initially, because that's a reactant, more initially than we have at equilibrium. So this here, 0.31 plus 0.17 will give us our initial concentration. Take that, multiply it by the volume of the container, 2.5 liters, and that'll give us moles of PCl5. And then, once we know moles of PCl5, we can use that to find grams of PCl5 using molar mass. So, pretty good problem there. A little bit different in terms of how we use our ICE table. All right, I mentioned before that we can use concentrations to find equilibrium constants. We can also use pressures. So when you use pressures to calculate equilibrium constant, technically that equilibrium constant is called Kp. Take a look at 1713. So instead of giving the amounts of each of the substances in molarity, moles per liter, we're given partial pressures. So we set up our equilibrium expression the same way. Instead of concentrations, we use partial pressure. So partial pressure of ammonia squared over partial pressure of nitrogen times partial pressure of hydrogen cubed equals our equilibrium constant Kp. Plug in our partial pressures and we get Kp, 7.11 times 10 to the negative fifth. Pretty simple. Go ahead and try that. Number 73 on page 698. So just like when we use concentrations to calculate Kc, we don't plug in our units. I want to just plug in units here just so you know these are not concentrations. These are partial pressures. In the future, do not plug in the units. Kc and Kp are both unitless. Just trying to show you we're using pressures this time to calculate the value of the equilibrium constant. Sometimes it's useful and necessary to convert between Kp and Kc. So I believe you have one of these forms on your equation sheet. So let's go ahead and do this. Oops, yeah. So R, of course, is our ideal gas constant. T is the Kelvin temperature. Delta N, as we see here, is the change in the number of moles of gas present. So technically, it has to be this way for this sign to work. It's moles of gaseous products minus moles of gaseous reactants. The other form, so this is if we're given Kc, we can use that to find Kp. What if we are given Kp and asked to find Kc? Looks pretty similar, except we have to the negative delta n. So multiply R times T times delta n. Now this is not based on the actual number of moles of reactants and products, but the relative number of moles of reactants and products from the balance equation in the reaction. So of course, if delta n is 0, RT to the 0 is just 1, then Kp is equal to Kc. I'm going to have to divide this lesson up into 2 videos, so next time I'll continue with example 1714 and some examples of how to go from Kp to Kc or vice versa. All right, thanks for watching. Stay tuned for the next video.